Greetings, my name is Cheyenne Valles, and today I am going to talk about the nonlinear effects of laser beat wave Wakefield acceleration near critical density for weakly relativistic and relativistic intensities in the first dimension. Again, my name is Cheyenne Valles, hailing from the University of Texas at San Antonio, and my mentors are Landry, Brian, and Ernesto. Moving forward, a little bit of background for laser pulses. So the following equation shows the electric field of the laser in the first dimension moving across z, as in the distance per se, over time. The first term in the equation represents a temporal envelope as a pulse duration of 1 over e of the height of the E field, or the electric field. The second term in the equation represents an oscillatory term that includes the central wavelength and frequency of the laser. So looking at the equation itself, we have t for time, z space, so on, and we can actually see in the picture to the right as a visual representation of what that equation actually looks like. We have the electric field represented in light baby blue color, and then the envelope as a dashed darker blue color. In order to actually see the corresponding values, we can look at it in terms of the E field as well as the intensity. And if we look a little closer, we can actually see a Gaussian of the intensity in the same graph. So next we need to understand what a laser Wakefield acceleration, or LWFA, is. Well, this is a process using high-intensity lasers to excite plasma waves. The plasma waves are then able to accelerate electrons to relativistic energies. Laser Wakefield acceleration can be achieved when a laser has a resonant pulse length equal to the period of the plasma Langmuir waves. Looking into the diagram on the left, we can actually see the electron being manipulated through the electric field caused by the laser pulse in the plasma. And a more realistic visionary that we can see in almost everyday life is the GIF to the right. It is a duck causing waves in the background. Those waves can be the wake fields caused by the laser, the duck being the laser itself. So just to put it into perspective, moving back to the picture on the left, the laser pulse is the leading duck, and the electrons behind it are the following ducks riding the waves caused by the leading duck. So moving forward, we can actually see the equation for the total full width half max as seen in the first background slide, and the plasma frequency. Also, we can actually see on the right a GIF for the spring and the conservation of energy and momentum. So moving forward, for the last background portion that we would need is the laser beat wave acceleration, or LBWA. This is a process using high-intensity lasers to excite plasma waves, similar to the laser Wakefield acceleration. So the difference between the two, it can be seen in the equation as well as the picture on the right. So to start off with the equation, we can see the carrier portion of it, labeled carrier, and the envelope portion labeled envelope. To put it into perspective, for the envelope, it is demonstrated on the right side at the bottom portion, and the carrier is as well. So first, how do we understand the beat wave in terms of laser beat wave acceleration? Well, the bottom left equation can represent the frequency of the beats using the first frequency minus the second frequency. Moving forward, you have the angular frequency, which is just 2 pi over time, equaling to 2 pi times the frequency. And putting those two together, you end up with 2 pi times the beat frequency equaling the angular frequency, which equals the angular frequency of the first set minus the angular frequency of the second value, similar to F1 minus F2. Moving forward, so laser Wakefield acceleration. Low density versus near critical density. Well, previous work has looked over the low density, where the laser moves at a constant of the speed of light, creates electron waves with near speed of light phase velocity, and it has fast waves but low amplitude. The near critical density research that I'm doing, however, you can see a drastic change in what we're actually doing in these two GIFs. So the first one, low density, low waves, surfers riding them. My research, however, it's like a surfer riding in a tsunami wave. Slow waves, but large amplitude. So the results, the figures left, middle, right show the laser electric field interacting with the plasma. This produces an EZ field. These figures have varying plasma densities of 0.1, 0.25, and 0.9 times the critical density. The waves of EZ are shown to increase in turbulence as the density increases, as well as being shown to increase as the density increases in terms of magnitude. So altogether, for the 5 trials that I did of different simulations, the increase of wavelengths as the density increases is represented to the right graph. This is shown by the 0.1 times near critical density line, which is the blue line, where there is one main peak at approximately 1.75 K over Kp, the normalized factor. Additionally, the 0.5 times near critical line, or the red line, shows multiple peaks with similar magnitudes. Some other results in a 2D graph. The 2D fast Fourier transforms in space are shown in figures 1, 2, 3, and 4 in relation to the plasma density. X-axis represents the normalized wave numbers, and the Y represents normalized frequency. In graph 1, we can actually see 0.1 times the near critical, and we can see very sharp plasmons in the value of 1 for the normalized frequency. The main plasmon here is looking to be at around -5 normalized wave number. If we look at 0.25 times near critical, we can see an abundance, but when we compare the two, there is more plasmons being represented in the graph than 0.1. And if we move towards 0.9 times the critical density, the numbers just keep duplicating. So with that being said, what we do like to see is the number of plasmons increasing as we get closer to near critical. Future work would be to look at more values, but also do previous work in the second dimension, and hopefully continue to enhance precision and efficiency in this field of research. I'd like to acknowledge the Trend program, mainly Daniel Serrano, the GradMap program people, for sharing their seminars and helping me understand various topics, especially to help in this research. My mentors, Landry, Brian, and Ernesto. My parents, most of all, for their endless support for one day helping me get to NASA. And below, if you have any more questions, I've added my LinkedIn, where you can find me at my home university, and my email, if that suits you. Thank you for your time. My name is Cheyenne Valles, and I hope you enjoyed this as much as I did.